Okay, so today is Holi here in India and in Mumbai. It's a big festival. It's a festival of colors welcoming spring. And you don't want to work on a holiday. Today is a holiday, at least in this part of the country. But I thought, uh, maybe I should show my audience how holy face looks like. So you go out, everybody is carrying some colors which wash off, it's organic and so on, and you put color on each other to celebrate the arrival of spring. And so this is how it looks. The clothes, everything is drenched in colors. And now that you got a look, you can decide what fun it is. You can find many videos, many songs are written about Holi, and very popular theme in Hindi movies or Indian movies and so on. So this topic is very nice, so it's appropriate for Holi, I guess. Calcite is as an efficient and low-cost material to enhance benthic weathering in shelf sediments of the Baltic Sea. So they have they did an experiment in the Baltic Sea. They measured various things to show that in fact calcite can greatly enhance benthic weathering and can be low cost compared to crushing things like dewlite or olivine to enhance weathering on soils. And there are of course enhanced alkalinity experiments being done in the open ocean to also enhance ocean uptake. It's called ocean CDR, ocean carbon dioxide removal. So recent studies have proposed calcite and dunite as possible alkaline materials for enhanced benthic weathering in shallow depot centers of the Baltic Sea as a marine carbon dioxide removal strategy. In this study, insights on calcite and dunite weathering from laboratory incubations and long-term bentocosm experiments are combined with a numerical box model to assess the carbon dioxide uptake potential of mineral addition to organic rich sediments in the southwest Baltic Sea. Very specific region and very specific experiment, but it's combined with numerical modeling and lab experiments to show that the results are quite robust, which enhances confidence as well. The results reveal that calcite has an up to 10-fold higher carbon dioxide uptake efficiency and is therefore preferable. It's therefore the preferable material for enhanced benthic weathering as a marine carbon dioxide removal method, with costs per ton of sequestered carbon dioxide ranging between 82 and 462 euro for calcite, while reaching 558 to 1920 euros for dunite. These findings could be applicable to other areas in the Baltic Sea and of course also globally to sediments in the wider coastal shelf with similar geochemical properties. If you want additional points, I would say doing things in the coastal region is much easier because you can monitor them well, and it's economic to transport things and dump there, and then you can also see if other co-benefits like enhanced fisheries, subaquatic vegetation, dissolved oxygen, etc. can happen, and they do measure these things. So I'm going to just skip all the details of the reactions, the box model and the experiments, and just show one figure. But let's read a bit for the motivation for trying this. Against the backdrop of increasing atmospheric carbon dioxide concentrations, a fast development towards net zero emissions is urgently needed, and for achieving this goal it's necessary to develop negative emissions technologies to account for residual emissions that cannot be avoided. So basically we can very easily justify that maybe efficient, effective and safe carbon dioxide removal methods are always a welcome part of the portfolio if we want to stay on course for keeping the warming as low as possible, keeping in mind the global warming targets. So basically ocean alkalinity enhancement has been one of the key technologies or approaches discussed a lot, and you have of course weathering of rocks in the ocean as well. On land also you can do enhanced weathering by crushing olivine or alkaline rocks and spreading them on the soil, and there are some debates about whether that can work or how long it can work and so on and so forth. And of course you have to do a life cycle analysis to see whether it's really removing additional carbon, more than what the energy being used and for crushing, transporting, and so on is involved. Apart from highly reactive hydroxides, calcite, a calcium carbonate morphotype, and dunite, a mafic silicate rock that mainly consists of olivine, have been suggested as possible materials for ocean alkalinity experiments. Both materials consume protons upon dissolution, increasing total alkalinity and subsequently leading to an uptake of CO2 in the water column and storage in the form of dissolved bicarbonate. As you know, ocean water has alkalinity that it tries to maintain on long time scales. So if you increase alkalinity, it's going to try to stay, kind of a homeostasis by taking up more CO2 and moving things between H2CO3, HCO3 minus, CO3 minus minus, and so on, and also enhancing weathering of the sediments. Just like weathering on land takes up CO2, enhanced weathering of sediments should also take up CO2, and it does, right? However, the abiotic dissolution of these materials in the water column is either chemically limited due to oversaturation in the case of calcium carbonates, or in the case of olivine and dunite, not feasible due to slow dissolution kinetics, then it's not very effective. So a more promising method then is to achieve ocean alkalinity enhancement using calcite or dunite, and this is enhanced benthic weathering as a way to do it, as opposed to just dissolving CO2 into the ocean water and then hoping it'll find its way out of the system. In this approach, the minerals are distributed directly into the marine sediments, whereupon dissolution is furthered as they are either exposed to grain collision in high energy environments or benthic weathering engine. The latter describes a combination of benthic processes where particulate organic matter is respired by microorganisms to CO2, thus lowering the pH of the sedimentary pore waters. Bioturbation and bioirrigation enable oxygen to penetrate deeper into sediments, further stimulating CO2 production and acidification. Besides the microbes catalyzing these chemical reactions, invertebrates in and digest sediments particles, where abrasion additionally contributes to mineral dissolution. Basically, the argument is that once you get down to the sediment with these calcite or dunite, there are processes naturally available to make them more soluble and enhance weathering. In the following, a combination of these processes will be referred to here as bioactivity. Okay, I won't read much more, but basically there are lots of publications coming along now, so we have to have good close knowledge gap that exists between assumed weathering rates and those that are actually valid in natural sediments. So you cannot just go from lab experiments to field experiments or large scales without knowing the real world conditions. So here the idea is to go from lab experiments into the actual field site in the Baltic Sea, as we said. So that's where they tried with the bentocosm, a word for benthic system, with the bentos, with all its ecosystems and physical mechanisms. So the latter are large plastic containers which they are using for doing this in terms of adding calcite and dunite to organic rich sediments of the Baltic Sea, and they are partly filled with sediments with constant flow through the Baltic Sea bottom water. So they are setting up some system to make this happen, and efficiencies and uptake potentials are then extrapolated to other marine ecosystems in their model. Marine systems, with similar geochemical properties as the Baltic Sea to assess global potential, and they provide some numbers on that, and they track the per ton cost as well, which is always a motivator to see what exactly is happening in terms of life cycle analysis and additional sequestration, etc. Let me jump ahead a little bit and show the figure. Here is the system. This is what they call the bentocosm, zooming into this region here. Kiel is over there, the very nice, what is the institute? I forgot already. Geomunda, something. Anyway, here is the Baltic Sea, the Kiel Bight, and there is Kiel, and you are in the region here. So you are taking in seawater pumped with filter into the header tank and seawater inflow into this box with half sediments and enhanced calcite or dunite for experiments, holes for pore water sampling so they can measure things, and then you have added alkaline materials, in this case calcite or dunite as we said, so that you can compare which works better, and then you put the seawater outflow back into the natural environment. So you have muddy sediments available in these regions. Boxes 1 and 2 are shown in these yellow things here, and box 3 is here for the data they are showing, and this big one, box 4, is in the green, which is part of the larger box, and Benthic experiments were done here. So it's a nice setup. It's a map of the southwestern Baltic Sea. Blue shading indicates bathymetry, so depth plots. Red areas denote the distribution of muddy sediments that we mentioned. Adjacent sediment consists of gravel and sand with low organic carbon content, so not much weathering to be done at fast rates. Yellow, red and green lines describe the approximate spatial extent of the boxes considered for the box model that I'm not going to get into, but you can follow up. And here yellow area is the area of application of the material for enhancing sediment weathering. The insert shows a schematic sketch of the benthic used for the long-term experiments, so the time series is long enough that they can actually make some conclusions. Here, identification of a candidate material for enhanced benthic weathering is important, and they give you some numbers, and we'll read in the last part that basically calcite works better, and they do some cost experiments. Figures are provided that I'm going to skip for brevity. I just want to get across the point that these are real experiments as opposed to open ocean pelagic water experiments with ion fertilization or enhanced alkalinity. These are about enhancing weathering in the sediments and in coastal regions, which are easily accessible, easily monitored, and so on. Okay, and potential co-benefits in terms of fisheries being, 90% of the fish get caught within about 200 miles of the coasts, exclusive economic zones, and so on. So dunite and calcite, both costs for production and grinding exceeded the transport costs by a factor of 5 for the coarser grain size. The implication being that proximity to the application site or the option for long distance transport via ships are key to extrapolate these pricing estimates to other application sites. So you have to be careful where you are going to do this and what the cost factors are, and of course energy, because every time transportation is involved, you are likely to involve other greenhouse gas emissions for the energy used and so on. In sum, the low cost CO2 uptake efficiency combined with the high energy demand for grinding exclude dunite as a potential material for efficient enhanced benthic weathering in the investigated study area. If this method sounds attractive enough, there will be others who will try this in other regions, and then we'll see if there are conditions that are different where maybe dunite can speed up the weathering rates just as much as calcite and give you cost-effective sediment weathering as well. For calcite, there are many constraints that do not apply that apply to dunite. Softer material requires less energy for comminution, which is the grinding up, and that lowers the costs and CO2 footprint compared to dunite, which is the crushed olivine. Okay, so I won't go into the numbers, but basically you get the idea that exact potential for enhanced benthic weathering and the precise threshold for high uptake efficiencies will need many more experiments. For that you can make actual comparisons of costs per ton and also comparisons with other carbon dioxide removal methods which are typically discussed during DACS, direct air capture and sequestration. And of course bioenergy, BECCS, is also always thrown in as a potential solution for staying within the global warming targets, but we know that bioenergy is going to compete for land and water and food prices, food security, etc., if we ramp it up as well. So let's then just jump to the last section. Enhanced benthic weathering in a global context. The results of this study clearly show that mineral dissolution can lead to considerable marine CDR, carbon dioxide removal, as long as the alkalized waters are in contact with the atmosphere to actually take up CO2. So you need a supply of CO2 from the atmosphere. Partial pressure of CO2 favors uptake, and if you have enhanced weathering, then the partial pressure is going to increase in a way to pump more CO2 into the water as well. These new findings have implications for the perception of EBW as a climate change mitigation measure. The Baltic Sea alone comprises 133,000 square kilometers of muddy sediment, so large area. Assuming a similar weathering behavior for calcite as in Eckernfond Bay, this would imply an uptake between 4.5 to 30 million tons per year, and the latter though is with lower efficiency. Okay, so despite the fact that the study area is rather small, a rather small inlet, the chemical features bear some similarities to large-scale upwelling systems where nutrient-rich waters foster high rates of primary production and organic carbon rain rates, which basically hopefully sinks to the bottom and disappears from the system for long enough time. The export of organic matter in such region leads to high organic carbon content in sediments that are similar to those in the study area of Eckernfond Bay. The degradation of this organic carbon combined with upwelling of PCO2 rich waters alters the bottom water chemistry in a way that makes these large systems comparable to the inlet investigated in this study. So there are details on why this should work. Thus, the presented results may well be extrapolated to a globally relevant scale, as the total area of the Earth's boundary upwelling systems alone accounts for about 1.04 million square kilometers, and that's a lot of fisheries as well. When including the highly productive East China Sea continental margin, the potential application area could be up to 2 million square kilometer plus several small-scale upwelling regions. Considering a higher but less efficient uptake of 320 tons per square kilometer per year, that's the rates they measured and come up with this number, and also including smaller potential application sites, annual global potential CO2 uptake might reach several gigatons. Now we are talking. We are always looking for gigaton CO2 drawdown, which will make it really a big part of the portfolio of solutions. It's not a silver bullet, and it shouldn't be used to continue fossil fuel burning, saying we are anyway sequestering carbon. That's not going to work. So there are many issues that are still out there in terms of exactly how this will play out in reality. So although it's unlikely that EBW will reach a potential to serve as a sole sink for global non-abatable CO2 emissions, it may well be an efficient way for countries bordering upwelling systems or organic rich shelf sediments to offset non-point sourced residual emissions or earn carbon credits, which is offset. Again, that has its own issues that have to be discussed, because if people emitting keep on doing this as offset, then they have less motivation to reduce their emissions, right? So there are all these moral hazards we have to worry about, but nonetheless, just in terms of doing the experiments in the lab, in the real setting, and providing measured quantities, doing box modeling and estimating global potential and cost per ton of CO2, and comparing two potential two potential solutions, calcite and unite, for enhancing alkalinity is a nice study, so I decided to include. Plus, this is such a hot topic that we should track them, and for those who complain I'm not an expert in this, I've done plenty of carbon cycle, but we have to stretch ourselves a little to see that, make sure that we learn what's going on for good and bad, and to make sure that solutions are something that we are aware of, so maybe we can build on them as well. Okay, anyway, enough of preaching, so see you in the next topic.